Welcome to Portland Cement Association Chapter 2 Ability in the course Construction 370 Concrete and Masonry from BYU-Idaho. This chapter provides an introduction to sustainable development and the concrete's role in that sustainability, using various systems of rating through our own sustainable efforts and through how we can use the product life cycle and analysis to find more sustainability on our construction job sites. What is sustainability? In a pioneering report from the World Commission on Environment and Development entitled Our Common Future, sustainable development is defined as meeting the needs of the present generation without compromising the ability of future generations to meet their needs. Embedded in this concept of sustainability is a balance of social, economics, and all environmental principles. The leading national recognized sustainability programs focus primarily on only energy conservation and atmosphere. Other water management and resources, site selection, and development of indoor environmental quality and material quality and its resources. Another factor that increasingly common in playing is functional resilience, or the ability of the structure to serve the original purpose and be adapted for future purposes. Several organizations have developed rating systems that attempt to quantify improvements in green performance. For example, concrete can contribute to credit in 15 categories in the United States Green Building Council's leadership in environmental and energy design for new construction and major renovations. The principles of sustainability development are easily incorporated in the design and the proportioning of concrete mixtures and exhibited readily through applications in service. The following list of items are all things that have been done in previous and will continue to be added in concrete sustainability. Durability, though, is the most important contribution of sustainable development. That characteristic by itself translates directly to the longevity of the structure. A structure that satisfies the needs of several generations is considered sustainable development. Also, concrete structures are disaster resistant. The home shown here survived a tornado in Wisconsin. So properly designed reinforced concrete is resistant to other storms, floods, fires, and other earthquakes. These structures can also provide blast protection for occupants that live therein. So the need to completely redo a structure after is reduced. Concrete structures also enhance energy performance. Concrete can enhance the overall energy performance in several applications, including the thermal mass, the fuel consumption, heat island reduction, and lighting efficiency. Insulating concrete forms shown in the picture provide thermal mass and high levels of insulation, key components for net zero energy use for structures and buildings. One of the key aspects of thermal mass is it can shift the energy demand to off-peak time periods as shown in this plot. For example, a building could be heated up during the daytime hours and then contain that residual heat in the cooler nighttime hours. Studies also demonstrate the lower fuel consumption for vehicles that travel on concrete pavements. Current research has shown that an increase between 1 and 11% for heavy trucks and 3 to 7% for smaller vehicles. In heat imaging graphs, this light-colored concrete material have higher solar reflectance, also called albedo, which reduces the heat island effect. The picture here shows a thermal image of a pavement transition in Mesa, Arizona. Note the temperature difference between the concrete pavement and the asphalt pavement. The SRI of new concrete greatly exceeds the threshold of 29 for most green building standards and rating systems. Concrete contains low to negligible amounts of volatile organic compounds. Decorative concrete flooring created using a sandblast stencil technique eliminates the need for carpeting and for other floor materials that can impair indoor air quality. Concrete can provide excellent acoustical control. The STC value is roughly the number of decibels that sound is reduced going through the wall. As cast, unfinished concrete has an STC rating from 44 to 58. If the wall is then dressed with furnings, insulation, and wallboard, the value jumps to as high as 63. In addition to building acoustics, concrete is used as highway sound barriers, and many methods have been developed to produce quiet concrete pavements. Pervious concrete allows for infiltration of water, reducing runoff from sites, and storage or collection of water. The image on the right shows a slide of water percolating through the pervious concrete. An alternative to pervious concrete is permeable grid paver system. The interlocking concrete pavers shown above allow water to infiltrate between the units and disperse between the base. Concrete structures can also provide green roofs. Green roofs can be made to support small plants, shrubs, or built to support much larger vegetation. Even metro gardens. The image shows here is the Chicago's Millennial Park, which is an extensive green roof covering a commuter rail station and 2 parking garages. Concrete cisterns collect rainfall and store it for later use in non-potable applications such as toilet flushing and irrigation. Treatment systems can purify the rainwater suitable for drinking, bathing, and other potable uses. Cement-based solidification or stabilization treatment is well suited for remediation of brownfields and has been successfully implemented in a number of brownfield sites around the country. Many concrete materials can be recycled after its initial use. Concrete from demolished structures can be recycled and is commonly reused as fill or road base. Paving trains can recycle existing concrete pavement. The crushed concrete can be used as aggregate in new concrete or as a base material. Many concrete structures already incorporate one or more forms of pre-consumer recycled materials in the form of industrial byproducts. Also, many cement plants utilize industrial wastes and discard tires as alternative fuels for the production of concrete in the kiln. Most of the components of concrete are manufactured within 300 miles of a concrete plant. Most ready-mix concrete plants are within 100 miles of a projected project site. These short distances minimize fuel requirements and the associated energy and emissions from the transporting and handling of concrete. During the life of a concrete structure, the concrete absorbs carbon dioxide in a process called carbonation. This may be viewed as a loop in the carbon cycle, as it's reabsorbed much of the carbon dioxide that was released during the calcination of the limestone in the cement manufacturing process. A key benefit of concrete is the ability to modify the concrete constitutes and proportions to best meet the sustainable goals of a particular application. So instead of having over-engineered mixes, a particular mix may be designed specifically for the performance requirements. Two examples are cement and aggregate. Both of these ingredients can utilize recycled materials. Life cycle analysis is a tool used to select building materials and influence design choices. A life cycle cost analysis is the practice of accounting for all expenditures incurred over the service life of a particular structure. So for example, a life cycle assessment, or an LCA, is an environmental assessment of the life cycle of a product or process. A life cycle inventory, or LCI, is the first portion of an LCA. It includes all of the materials and energy inputs as well as any emissions to air, water, and land from the various stages shown in this graphic. An LCA provides a consistent methodology applied across all the products and at all stages of their production, the transporting, use, and recycling at the end of the life or of disposal. This table shown here demonstrates the life cycle phases and the components of concrete pavements. This table demonstrates the life cycle phases and the components of concrete buildings. So in summary on this chapter, the LCA, for example, of the MIT Concrete Sustainability Hub at the Massachusetts Institute of Technology Concrete Sustainability Hub, a team of professors, researchers, and students are using LCA to evaluate and improve the environmental performance of buildings and pavements. Preliminary analysis from this MIT study indicated that the operation components of the infrastructure, primarily the heating and the cooling systems for buildings and rolling resistance for pavements, hold the most potential for large-scale improvements. So in summary, concrete products have a vast array of sustainability in which we can earn points through rating systems, use sustainability practices in our job sites, and then track that benefit through the life cycle analysis. Please remember to add questions into your learning journal as you explore the ideas of sustainability of concrete.